Hi, this is Stan Lyle with MasterMath. During the lesson, you're going to come to some You Try It slides where you're asked to do problems that relate to the lesson. Hit your pause button, try the problem, and then hit the forward key to move on to the answer. I hope you have a really good time today. In this lesson, we're going to review linear functions, exponential functions, and quadratic functions. And we're going to compare and graph them. Now, a linear function is a function that could be written in this form: y equals mx plus b, where m is the slope, or the rate of change, and b is the y-intercept. An exponential function is a function that could be written in this form: y equals a times b to the x power. And a quadratic function is written in this form: y equals a times x squared plus bx plus c. Each of these types of functions graphs differently. A linear function graphs as a straight line. If we use the example y equals 3x plus 2, we'd get a graph that was a straight line with a slope of 3, and it crosses the y-axis at positive 2. As an example of exponential functions, let's use y equals 3 times 2 to the x power. You can see that as x increases, y increases faster and faster and faster. We start to get exponential growth, and the curve looks like this. Let's look at quadratic functions. But we're going to have to simplify this a bit for this exercise. Let's pretend that b equals 0 and c equals 0, so that our quadratic function is just y equals a times x to the square power. And here's an example: y equals 3 times x squared. The graph for that looks like this. It's a parabola. Let's focus on linear functions for a minute. The graph on the right represents the linear function y equals 3x plus 2. This table also represents the linear function y equals 3x plus 2. And the points in the table are the points that I've marked on the graph. Well, now I can look at the graph, or I could look at the equation, and I could say this is a linear function. But what if I didn't have the graph? And what if I couldn't see the equation? What if I could only look at the table? Could I tell it was a linear function? Well, yeah, we can. And here's how we'll do it. When we look at this table, we see that there's a constant rate of change. We can see that as my x increases by 1, my y increases by 3. Maybe it'll be a little easier to see down here. When my x goes from 0 to 1, my y goes from 2 to 3. And then x increases 1 more to get to 2, and y increases 3 more to get to 8. My differences in my y values increase at a constant rate of change. For an increase of 1 in x, I get an increase of 3 in y. That means my slope is 3. My rate of change is 3. So my equation, y equals mx plus b, could be changed because I know m. I could call this y equals 3x plus b. Well, now all we don't know in order to finish this equation is b. But I do know a bunch of y's and a bunch of x's. They're all lined up over here, and I could use any of them. Why don't we use 2 and 8, because it probably is going to be easy. An x value of 2 and an 8 value, or a y value of 8, could be substituted into this equation, and then we could solve it for b. 8 equals 3 times 2 plus b, 8 equals 6 plus b, 8 minus 6 equals b, and b equals 2. So now we know what m is and what b is, and we can rewrite this equation y equals 3x plus 2. Let's take a peek and see if that's the equation we started with. Oh, it is. Y equals 3x plus 2. Now you try this one. Hit the pause button, do the problem, and then hit the forward key to move on to the answer. Well, I gave you a hint here. I put a column in marked difference. But hopefully you saw that there was a constant rate of change. That for each increase of 1 in x, I was getting an increase of 2 in y. When I went from 0 to 1 in x, I went from 3 to 5 in y. So my rate of change is 2. Now I can fill in the generic equation and write it as y equals 2x plus b. And now I can input an x value and a y value and solve for b. Why don't we use some easy ones? Let's use x of 0, y of 3. And then we can rewrite the equation 3 equals 2 times 0 plus b. Or 3 equals b. Well, now I know m and I know b, so I can write my equation. Y equals 2x plus 3. Now let's look at exponential functions. How about y equals 3 times 2 to the x power, which is graphed on the right. And you can see this is showing exponential growth. Increases in x result in increasingly greater increases in y. It's showing exponential growth, and it's an exponential function. This table of data also represents the function y equals 3 times 2 to the x. Now let's do the same exercise we did before. What if we couldn't see the graph? And what if we couldn't see the equation and only could see the table? Could we calculate what the equation was and determine what kind of function we were looking at? Well, yes, we could. Now we first might want to start by figuring out what the differences in y were with a change of 1 in x. And if we did that, we'd see that we don't have a constant rate of change. That rate of change keeps increasing as we move increasingly towards larger x values. So we know it's not a linear function. So next we might look at what the ratio of changes in y are. How much does y change as a multiple of the previous y? Well, if we look down here, we've got an increase of 1 in x, and y doubles. It goes from 3 to 6. And here we've got an increase of 1 in x, and again y doubles. X increases by 1, y doubles. The ratio of y's is 2. And that tells us that we're looking at an exponential function. That 2 is the number that's being raised by a certain power as x increases. So we know that our generic equation, y equals a times b to the x power, would start out with y equals a times 2 to the x power, because 2 is the ratio of change for an incremental change of 1 in x. Well, now we could substitute x and y values from our table and figure out what a equaled. Let's start with some easy x and y values, 0 and 3. I'm going to substitute 3 for y and 0 for x, and the equation becomes 3 equals a times 2 to the 0 power. Well, 2 to the 0 power is 1, so 3 equals a times 1, or a equals 3. Now I can write my complete equation. Y equals 3 times 2 to the x power. And sure enough, that's the equation we started with. You try this one. Hit your pause button try the problem, and when you're finished, hit the forward key to move on to the solution. Let's first look at the rate of change in our y values. As I move down the table, my x values increased by 1. What kind of change do I get in my y values? Well, from a y of 2, I go to a y of 8, or an increase of 6. But the next step, from 8 to 32, is not an increase of 6. It's an increase of 24. So there's not a constant rate of change. And this is not a linear function. Is it an exponential function? Is there a constant multiple of change? Well, let's find out. When I go from a y value of 2 to the next step, a y value of 8, that's a multiple of 4. When I go from a y value of 8 to a y value of 32, that's also a multiple of 4. My ratio of change is always 4. So this is an exponential function. And I know that my b value is 4. Now I just got to calculate my a value, and I'll do that by taking this equation, y equals a times 4 to the x power, and I'll substitute x and y values from my table. Let's use 1 and 2. X equals 1, y equals 2. 2 equals a times 4 to the first power, or 2 equals a times 4. I divide both sides of this equation by 4, and I get 1/2 equals a, or 0.5 equals a. And I can substitute that value into y equals a times 4 to the x power, and I get y equals 0.5 times 4 to the x power. Now let's go through the same exercise for a quadratic function. And we use this example, y equals 3x squared, which I've graphed here. You can see it's a parabola. It's a quadratic relationship. And this table represents the quadratic relationship. These points are the points that I've marked on the graph. Well, what if we couldn't see the graph? And what if we couldn't see the equation? What if we only had the data in the table and were asked to figure out what type of function was shown and what equation represented that function? Could we figure it out? Well, we'd first want to start by finding out what changes in y we got for a change of 1 in x. We'd want to figure out what our differences in y's were. And when I do that, I can see it's not a constant rate of change. The change is changing. It's varying each step. So it's not a linear relationship. Is it an exponential relationship? Well, I don't think so. And here's how I could tell. Are my y values changing by a constant multiple? When I go from 3 to 12, it's a multiple of 4. When I go from 12 to 27, it's not a multiple of 4. So this is not an exponential relationship. Well, to prove that it's a quadratic relationship, what I have to look at is the second level of change. How much does my difference in y values change with an incremental change of 1 in x? Well, when I go from minus 27 to minus 21, I've added 6. When I go from minus 21 to minus 15, I've also added 6. When I go from 3 to 9, I've also added 6. So my second level of change is consistently 6, and that proves that this is a quadratic function. Now I just got to figure out what that a value is. And to do that, I'll substitute a pair of xy values into that equation and then solve for a. Let's use some easy xy values. An x of 1, a y of 3. 3 equals a times 1 squared. 3 equals a. And now I can write the equation. y equals 3x squared. And sure enough, that's the equation we started with. Try this one. Hit your pause button, do the problem, and then hit your forward key to move on to the solution. Well, the first thing we want to do is calculate what changes in y we get for a change of 1 in x. We want to find out what the differences in our y values are as we move down the table. And when we do that, we see we don't have a constant rate of change. This is not a linear relationship. Is it an exponential relationship? Well, let's see what multiples we have. Do we have a constant multiple? When we go from 2.5 to 10, that's a multiple of 4. When we go from 10 to 22.5, that's not a multiple of 4. So this is not an exponential relationship. Now let's see if it's quadratic. What are our differences as we move down the difference column? When we go from 22.5 to 17.5, that's a difference of 5. 17.5 to 12.5, also a difference of 5. We've got a consistent second level change of 5. So we know this is a quadratic relationship. So now we can use our basic quadratic formula, y equals ax squared, and substitute some x and y values into that to calculate what a is. Let's use 2 and 10. Y equals 10, x equals 2. So 10 equals a times 2 squared. 2 squared is 4. Now I need to divide both sides of the equation by 4 to determine that a equals 2.5. Now I can substitute a, or 2.5, back into my generic equation, and I get y equals 2.5 times x squared. And if I graph this, it looks like a parabola. And since I have since my b value and my c value are both 0, it's a very simple quadratic relationship. The vertex is at the origin. That's our lesson on comparing linear, exponential, and quadratic equations. I hope you learned a lot. Now it's time to test your skills. Go to www.mastermath.info and you'll find worksheets and quizzes and cool links there to help make sure you understand this concept well. Well, I hope we see you again real soon. Bye-bye.